Hello and welcome. Today we're doing some undergraduate stuff. So I'm going to revise complex integration. I've got 5 bullet points, so I'm assuming you've seen stuff like that before. Perhaps you have forgotten, perhaps you need a little bit of polishing off. And my intention is perhaps to eventually evaluate some real integrals using complex numbers and possibly some series eventually with these kind of things. So the first 3 lectures, one is going to be revision, the second one possibly compute some Lorentz series, and the third one possibly evaluate some residues, and then we're going to go to what our eventual intention is. Okay, this lecture is obviously undergraduate level. It will be helpful for engineers, scientists, physicists, and even mathematicians will find this fairly useful perhaps. I'm not going to do things in a formal way, in a rigorous way, so please forgive me if you're a purist. I'm going to do things in an applied manner, a lot of hand waving in all of this kind of stuff. Okay, so let's get going. Let me just sort this mic. It's got a very long cable. I hope the sound is okay, because this is it's been a problem in recent lectures. Okay, so let's start first of all by looking at this special integral. What is this special integral? Okay, let's look at the integral of z minus c to the power of n dz around a closed path, which I'm going to define in a minute. So some kind of contour. Contour is just a specialist name for a path. And let's say c here is a complex number, and that's why I'm using the letter c for it. And n is an integer. Okay, so no fractional powers there, but it could be negative, of course. And let's say the path of integration is going to be around a circle, which is going to be located. I'm not going to draw axis. Oh, actually, I'll draw the axis afterwards. So this is the point C, and this is my circle, traced in an anti-clockwise direction, and I'm going to put some axis perhaps here. It doesn't matter what the C really is. So that is imaginary Z, real Z, and what should the size of the radius of the circle be? Let's say R, capital R for the radius. Of course, R is a real number. Okay, how are we going to integrate that? Of course, we need to parameterize the circle, the curve. So this is my gamma, by the way. There, the standard parameterization is going to be let z, in order to lie on this circle, be equal to c plus radius e to the I theta, where theta will be running from 0 to 2 pi. I'm going to have to speed up a little bit later on, guys, because I don't want this lecture to go too long. So if I start talking a little bit too fast, please forgive me. Okay, I need my dz. So dz is going to be equal to c will disappear, so I'm going to have I r e to the I theta d theta. Okay, so I'm going to start putting things in. So this is basically now will become a gamma of theta if you want, after the parameterization. So putting stuff into my integral, this will become the z is c plus r e to the I theta minus a c from there, all to the power of n, and I didn't leave enough space, very bad planning. I'm gonna have to rub off a little bit of my axis there, hope you forgive me for that, just to fit my dz, and my dz is I r e to the I theta d theta, and let's use a bracket, and let's tidy this up a little bit. So what do we get? Okay, so the c's will cancel there. So I'm going to get, first of all, let's pull outside the integral all the constants which are independent of theta. I've got an I here, so that's that I. And I didn't leave enough space again for the R. Okay, R to the n from this bracket, and I got another R from there, so it's R to the n plus 1. I would have pulled it outside, but I left no space. So I'm going to leave him inside for the time being. So that's going to be R to the n plus 1, and pull it out on the next line. So E is, I'm going to have E to the I n theta, and I got another E to the I theta, d theta, little bit of a tidy. So I'm going to have I r to the n plus 1, outside the integral. And this quantity here now will be, I'll write it as a single exponential. So it's e to the I n plus 1 theta d theta. And let's think about this integration and what we're going to get for that. Equal, it's a very simple integration because exponentials integrate very nicely. That's going to be IR times 1 over I n plus 1 square brackets. Oh, I forgot the limits throughout this. Oh, wow. Okay. Theta is, of course, 0 to 2 pi. We did mention it there, but I'm very, very, very bad. I didn't put them anywhere. I just realized I need limits once I go to the evaluation. Okay, so, and that's the exponential e to the I n plus 1 theta between 0 and 2 pi. Okay, is there a problem in evaluating this? Yes, there will be a problem potentially. The problem is if n is equal to -1. So this we cannot really consider. So going back to the very beginning, we're going to say n belongs to z here in order to proceed, but n cannot equal to -1. So for the time being, we're going to come back to that. For the time being, n is not -1. So this thing here, we're not dividing by 0. Okay. So what will we get for this particular one? The i's will cancel. So I'm going to get r over n plus 1. And now I'm going to put my limits on this expression. So this is e, the 2 pi I'm going to write here as 2 pi I bracket n plus 1, and minus, when I put 0 for my theta, e to the 0 is 1. And I'm going to need to evaluate that further. Let's make some room. Let's leave the top line. So, and let's, I don't need that line either, it's a bit off. So that's gone as well. And this will now give me equal to r over n plus 1. And now the question is, what is that? It's probably better to actually say to change into sines and cosines. So this is by using Euler's formula, or Euler's theorem, whatever it's called. Cos of 2 pi, that's the argument of the cosine, 2 pi n plus 1 plus I of exactly the same argument, sine of 2 pi n plus 1. That's the exponential. And of course, we've got the -1. Let's not forget this. And let's see what happens now with this expression. Does it simplify nicely? We're going to have r over n plus 1. All good. Cos of multiples of 2 pi, integer multiples of 2 pi. So cos of 2 pi, cos of 0 even, cos of 9 pi, it's not 9 pi, 10 pi or whatever, will of course give me 1. I forgot the 1 there. It's minus what? -1. Okay, so it's going to give me a 1 for all integers because it's multiples of 2 pi. However, the integer multiples of pi or 2 pi will be 0, so it's going to be 1. This of course will give me 0, and -1. Let's put the minus like this and rub off the plus I've just written there. So of course we have a very bizarrely, this is actually equal to 0. So what we just found is this particular integral over a circle radius r, okay, centered at C, for all integer powers of n except -1 gives me 0, which is quite interesting. Okay, so we'll come back to that. And first of all, let's examine what happens if n is equal to -1. Okay, so the parameterization is exactly the same. It's just I'll probably write a little bit different when it comes to do it. So let's look at the special case. Let's clear the board first of all, and let's see how that changes things. Okay, is it doable, or do we have a problem? What's going on? Probably this, I will write it, is to the -1 now, so that's the special one. Okay, and I'm going to write it first of all, for simplicity, as 1 over z minus c dz. And we're still on the same circle, and let's see what happens. Okay, close curve. So we're putting now our bits in. So that's from theta is equal to 0 to 2 pi. This time I remembered the limits. 1 over z. Z is of course c plus r e to the I theta minus the c, and my dz is of course I r e to the I theta d theta, and see what happens. The c's will cancel. And now let me just write that, squeeze it here, although it should be obvious what I've got remaining. I'm going to have an I r e to the I theta. That's from this bit here. The d theta I'm going to leave at the end here. And on the denominator, I've got r e to the I theta. And these two things will cancel. I still got an I. So this will give me I 1 d theta, limits 0 to 2 pi. And this, of course, will give me I times 2 pi, or 2 pi I. So it's very special and very unexpected. So when I have integers, okay, this particular integral actually should have been n there from the beginning. Actually, let me write it on the top right now. I don't need this. So I'm going to collect these results and just leave them on the top right of the board. So what we found so far is the integral of around a circle of radius r centered at c of z minus c to the power of n dz, where c is a complex number and n is an integer. Okay, this produces 0 if n is not equal to minus 1. However, the very same integral, if it's to the minus 1, again, same path with respect to z, gives us 2 pi I. This is a very special result, and of course, we often see it without the c. So, of course, it goes without saying, I'm going to write it in red. So if you had z to the n, or z to the minus 1, or 1 over z, oops, I was about to write x there. Okay, it will still be giving you exactly the same thing. So if you have integer powers apart from minus 1, this reduces to 0. However, the power of minus 1 is very special, and this produces the answer of 2 pi I. So this is the first result, a very special integral. Then we're going to look at singularities. What is singularities? First of all, it's it's a special word for saying kind of asymptotes in the complex plane. In the real with real numbers, when we're dividing by 0, we're getting vertical asymptotes. In the complex plane, when we're dividing by 0, we get sort of irregularities, if you want, which we know as singularities. It's the equivalent of the asymptotes in the complex plane, if you want. So first of all, let's see what kind of singularities, what kind of asymptotes, if you want, we're getting with complex functions. Okay, so first of all, just an elementary classification. We have first of all three situations. So no singularities. So a function f of z can have no singularities, or / removable singularities. Not the same thing. Removable singularities. So that means basically when you look at the function, we don't really divide by 0 as such anywhere. So examples of that, I'm going to put e.g. the function f of z is equal to z cubed. It doesn't have any singularities, okay? We're not dividing by 0. It's all nice everywhere. What about the function cos z? Or is also fairly straightforward. What is a removable singularity? If we look at, as an example, a very simple example, sine z over z. At first glance, we might be thinking, well, when we divide, when z is equal to 0 at the origin, we have a problem. It's we're dividing by 0. But in fact, we're not as such, because if you think about the Taylor expansion, or the Maclaurin expansion, whatever you call it, of sine of z, which is, I'm going to write it here, z minus z cubed over 3 factorial, call it 6, plus dot 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 over z, which is there, all the z's can cancel all the way through. So in fact, this division by 0, if you want, vanishes, and therefore there's no really a singularity in this particular function. So this is a removable singularity, okay? So this is the first type of situation we can have with complex functions. So we're going to go to the second one now. The second type is this kind of singularities are called poles. Poles of some order. What does that mean? We'll explain again. We have, for example, simple poles, simple, double, triple, etc. After a certain point, we just say a pole of order 6 or something like this, but we're going to say quadruple, I guess. So what is a pole of a certain order? Let's say like a simple pole. It's probably easier to see it through examples and get an intuitive idea just by looking at the function. What do we mean by something like that? So suppose we have f of z is equal to, and let's put a, for example, a cos of 2z divided by z, okay? This does not vanish, it's not like the sine z over z, so it's not a removable singularity if you want. And we're dividing by just z to the power of 1 if you want, okay? So this will be a pole at the origin, of course, because z it has to be 0. Pole of order 1, or just simply simple pole at the origin, okay? What about if we had a different one? For example, I'm going to put a 1 over, and let's put z plus I in a bracket, and here I'm going to have a z minus 2, but the second bracket, let's say, is squared. It's not removable quite clearly. So here we have, looking at the denominator, we can actually produce 0 on the denominator in two different cases. When z is equal to minus I from this bracket here, okay, we have a singularity. This is a simple pole again, simple pole. But this, however, when z is equal to 2 on the real axis, we also are creating a problem. However, because this bracket is squared, that's an intuitive way of thinking about it. This is a pole of order 2, or a double pole at z is equal to 2. And one third example, let's say we have, I'll keep it on the top, just a single number, just to keep it nice and simple and get the idea. Suppose you had a z squared plus 1 in one bracket, and you had a z minus 4 to the power of 3. Okay, what are the problems here? First of all, this bit here, remember we're on the complex planes, therefore this does factorize. You kind of create zeros there, so it's probably better if we write it as a difference of squares, if you want, as z plus I and a z minus I. Okay, so that's the factorization of that, if you want. So quite clearly, this particular function will have a simple poles, so simple at z is equal to plus or minus I, and we have a triple pole, at z is equal to 4. Okay, so this is an intuitive way of thinking about poles of some order. When we do Laurent, there's some different interpretations for all of this, so we're going to come to that eventually. And then we got, I don't know if we can see the board if I write about here. I hope we can, because not a lot to write. So there's a third type of kind of singularity. This is the ones that are of interest to us really for most of our work, and also these ones we're not going to do a lot for what we're about to do and what I'm about to show you in the few lectures later on. We have essential singularities, essential singularities. What are these? These are very bad singularities. I'm just going to give you an example. We're not going to be spending much time on that. So this is really something, for example, e.g. f of z, okay, is e to the power of 1 over z perhaps, or something like that. Okay, this is a real problem. It's not a pole. We're going to look in a minute at we're going to discuss something like that perhaps in a minute when we're going to look at power series, which I got up there. So this is just an elementary classification of singularities, and I hope you got the idea about the poles more than anything at this level. First of all, just by looking at it and just being nothing formal about what a pole really is in complex in a complex plane. So we're done with the singularities. So that's the second thing I wanted to revise. And the third thing is power series. So what I'm going to do is I'm going to perhaps use a little bit of space here to actually talk about the real numbers. First of all, a function f of x now, okay, a real function, will have what is known as a Taylor series. Taylor series, or if you're expanding about the origin, is called normally a Maclaurin. I think I'm spelling correctly, so I do apologize. My spelling can be very, very bad at times. English is not my first language. So, and of course, for that to happen, the function must be infinitely differentiable, and then we can have one or the other, okay? In the complex plane and with complex functions, we've got kind of similar things with slightly different terminology and a few extensions. So first of all, if we have this case here, we have no singularities or removable singularities. Now the f of z, or any of these functions here if you want, will have a standard Taylor series, which will look something how you know it in the real with real numbers. There's some kind of coefficient a r z minus some complex number to the power of r, and it will run from r is equal to 0 to infinity. Okay, so it could be, of course, I'm going to put there slash ar z to the r, which is like the complex Maclaurin, but I don't think the term Maclaurin is actually being used at all in the complex plane, so we still call it a Taylor series, I think. Just conventions really, possibly for historical reasons, or who knows. Okay, so this is what happens with if the function, the complex function, has no singularity. It will have a normal Taylor expansion. Okay, what happens now if we have poles? Okay, so this is now when things become a little bit different, a little bit more interesting perhaps. Okay, so let's rub off these examples. So suppose we have a pole of order 1. Pole of, actually I'm going to write simple pole, okay, it's easier. Simple pole. I'm going to write it explicitly here. We have a power series. You can still call it a Taylor, but it has a special name. And I didn't write it up here. It's called a Laurent expansion. Okay, it's a French guy. I'm pronouncing the name the English way. If you're French, please be. I hope you're not offended. So a simple pole. Then the f of z will have a power series. I'm not going to write it like this. I'm just going to write it explicitly, write a few terms so you can understand what does it look like. For a simple pole, your power series will start from something, I'm going to call the coefficient a minus 1. And just to keep it simple, it could be, of course, z minus a. But of course, let's keep it simple and say all these expansions are about the origin. So we're just going to keep it as z. So it's going to start with a minus 1 over z plus an a0 plus an a1 z plus an a2 z squared forever, dot, 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 like the normal power series, like the Taylor. What about if we go a double pole? What does this power series known as Laurent will look like? Well, you can guess perhaps what it will look like. This time your f of z will be starting with one term to the left, so it's going to be a minus 2 coefficient if you want, and again I'm going to use just z's for simplicity. So we're going to have a minus 2 over z squared plus a minus 1 over z plus the a0 plus a1z dot 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 forever. And you can guess, I'm going to put one more. What if you have a quadruple? Oop, I'm not changing it. It says quadruple there, by a P. So it's a bad P. Okay, so this one quite clearly it will be starting from the power of z to the 4 at the bottom, coefficient a to the minus 4, plus a minus 3z cubed, and so on. So poles produce this type of power series, and the order of the pole determines how the Lorentz, how the power series of expansion starts. Where does it start? And that leaves us, of course, now what does the power series for something that has essential singularities look like? Okay, this, I guess, maybe you can guess what it will look like. This particular Lorentz, I'm not going to write it explicitly. I'm going to write it in sigma notation. It basically starts forever to the left to infinity, okay, negative infinity, and forever to the right, positive infinity. So you can think of that as a Taylor series with two branches, one to the left and one to the right. So in general, it will be a sum which will run from r is equal to minus infinity to infinity, and some coefficient a r. And if you want to do it in z, you can do it in z. If you are expanding it by a different point, of course, it'll be something like this. So from minus infinity to infinity. So this goes on forever. For what we're about to do, as I said, this is not important for us. I'm sure purists will find interesting thing to do with absolutely everything here. We basically will be concerned with this type of power series. Okay, so this is now the third bullet point done. Lorentz is now finished, and we're gonna look at deforming curves. Okay. The other day, a few lectures ago, I was doing some line integral, and a little bit of complex numbers came into it, and I did say by, I think it's called the Deformation Theorem, and I was a little bit embarrassed because it's been a long time since I taught any of this kind of stuff, and even longer since I was last taught this kind of stuff. I thought to myself after the lecture, I'm going to go and check it out. What is it called? The Deformation Theorem? Or does it have anything else? And to be quite honest with you, I've totally forgotten, and I haven't. So do forgive me if I'm going to call it still the Deformation Theorem, but it might be having a name, and it's exactly the same thing. You'll see from the context basically what is happening. Okay, so this is the situation. Suppose we're on the complex plane. I'm not going to draw any axis. There's a singularity. So let's say a simple pole. It doesn't really matter what it is. Some singularity. Okay. So and at the moment I want to integrate around this particular singularity, and let's say we're having something which looks like this, and that's our path. It looks like a keyhole or something. So let's go in an anti-clockwise direction. So the question is, what is the answer to this particular integral? So we try to do basically the integral around this closed path. This is our curve gamma, and the function we're integrating is f of z, and this function, let's say it has, for without loss of generality, let's say a simple pole at this particular point, which is inside the path of the integration, dz. Okay, this is what the Deformation Theorem says. It says, and let's say there was another singularity somewhere. This singularity, let's say, is up here. So this function has also got singularity up there. Let's say another simple pole, could be double, it doesn't really matter. What the Deformation Theorem says is we can actually change the shape of this particular contour, let's say to a nice curve, perhaps a circle. I'm going to draw it, unfortunately it's going to be very, very small. I'm drawing it in red. That goes also in an anti-clockwise direction like the original curve, and it contains still the same singularity, the same pole that was inside the original curve. It does not include that. So the answer for this particular integral around this gamma, okay, is going to be around this curve gamma dash. We get exactly the same answer. So why we want to do something like that's quite obvious. I mean, this is a mess here. Well, I cannot even parameterize something like this, but it'll be much nicer to go around a circle, which I can do an easy parameterization. So it helps us change paths contours, close contours to something which is more doable. Circles is usually a good example. Sometimes we go ellipses. Other curves that are of use are sort of rectangular curves, often used for rectangular or square curves for hyperbolic, for integrands with hyperbolic bits. For summations, we use square contours. Semicircles with, I don't know, with a straight bit like that, or semicircles with little indentations. Keyhole contours, which will look something like this when we're having branch points. So we're gonna get very, very bad, something like that. So it allows us to actually change the shape of the curve. The important thing is, whatever curve we change to, it contains exactly the same singularities, none removed and none added. So if I go around this particular shape, I still have inside the same singularity that I marked here, and I haven't included. I cannot go around this one. That will have a completely different answer because I'm including this bit here. Unless there is a special case, just in case I say not always, unless, as I said, it's a special case. If suppose the residue of this was actually 0, then it will not add or contribute anything extra. But let's not think about silly things here. We'll look at the normal sort of case. So this is the deformation theorem. And if you think about what we were doing up there, that's why I said it doesn't really matter if where the circle is, as long as it contains the singularity which there was at C, it will still work. So this is what we are allowed to do, which is very, very helpful and very, very useful. So the last bit I want to finish off with is just an informal treatment of what we're about to do eventually. So let me just finish off by doing a very bizarre sort of integration, if you want. So I'm going to integrate an f of z dz around some curve gamma. Okay, and let's say, what is that particular f of z? It doesn't really matter. And what is this gamma? Let's say our gamma, I'm going to draw it here, is some kind of rectangle which looks something like this. And I'm going around it in an anti-clockwise direction. And let's say we have a singularity here. That's the singularity of f of z. It doesn't really matter what it's a pole, let's say, of order 5, I don't know, order 2, it doesn't really matter. And I want to evaluate this particular integral. Okay, what can I do with this particular one? Okay, first of all, I can actually write my f of z, let's say, as is Laurent expansion. What is the Laurent expansion? I don't know what it is. Let's put speech marks, Laurent of f of z dz. Very nice maths. Okay, so what will that mean? It will mean we will have something. What pole did I say had? I don't know, I can't remember now. Let's say I'll make up an expansion just to get the idea. So suppose we had a 3 over z cubed minus 5 over z squared plus 2 over z plus 7 plus, I don't know, z plus z squared dz, and so on, dot, dot, dot there, of course. And what I want to do now from this particular line, okay, how can I integrate that around this square contour? Remember now the deformation theorem, I can actually deform the curve there and say, okay, how about if I pick a circle of radius r, which we parameterized up there, okay, and do something like this. So that definitely will give me the same answer. So all of this will be parameterizable. But then wait a second, we have these special results, and I said here is in z, there was in z minus c, but you can see I wrote there in red these quantities here. If I integrate perhaps term by term my expansion with respect to z, any power of z, integer power of z, with the exception of this special power, the 1 over z power if you want, this will have 0 contribution. All of these integrals will be actually equal to 0. And therefore, the only thing I need to integrate is the 2 over z, which is going to be around this new curve. Let's call this gamma dash if you want. Okay, and that was the original one. The square contour was the gamma there. So I can actually do the following. I can say, okay, I'm gonna go on the little circle, gamma dash. All of these things are goodbye, and I need to integrate 2 over z dz. This 2 I'm gonna pull outside. Let me just do it here actually. 2, 1 over z dz. And of course, this is the special integral that I've got up there, and this gives me the answer of 2 pi I. So I'm going to have a 2, which I pulled outside, times 2 pi I, which of course it'll give me 4 pi I, and this is my answer for this particular f of z. I didn't put just a general example. I don't know what the function, just a general result. So this is kind of, perhaps you can think of it as what your residue theorem says, and how I personally see it in an intuitive way. Again, no formal proofs, no punctured discs, and none of this sort of formal things that we see in complex analysis. So that's the fifth and final item, putting things together. So what I'm going to do, that's the end of the lecture, guys. Okay, what I'm going to do, I hope to do another lecture number 2, which will be computing some Laurent series for some functions, of some known functions, just to get us the idea of how to find Laurent, and then possibly one more in computing residues, which I will mention what is a residue, because I haven't actually mentioned what is a residue here. I should really perhaps have mentioned what is a residue. And then after that, we have enough in our toolbox to perhaps look at real integrals and summations, and just do some applications which are practical in applied mathematics. Okay. On that note, who's laughing now? I'm laughing because it's 1 a.m. at the moment, and I'm going to my bed. I hope you found this useful, and join me again real soon. Okay. Bye for now.